Hello, y'all. This is Darrell Lee Berry Jr. back with some more linear algebra. As promised, I'll go ahead and find four fundamental subspaces to make sure I don't make a matrix that is not, not able to be reduced properly. I'll use a matrix that we went over in class that our professor used to make sure that I get the right answers, and that is the matrix that works. And I'll go ahead and use that to uh, share what I'm going to share. So we'll go ahead and get started. Go ahead and I'll just go straight to the screen share. And this will be the matrix that we'll do. And to confirm, we want to find the column space, the null space, the row space, and the left null space, which is the null space of A transpose. So what we want to do, if we want to find the null spaces, it seems like the best thing to do is to start with an augmented matrix, except instead of zeros on the side, we have the B vector, which is usually the um, sort of standard or customary input for the constraint equation. Remember, we're trying to find the constraint equation. This is what we'll basically solve for B. So basically, if we want to go from uh, vector notation of a plane to Cartesian notation, the constraint equation, when we solve for the constraint equation will give us that. So the constraint equation, when you have a row that equals 0, the constraint equation is the plane in Cartesian. So remember that from one of my previous videos. So the first thing we're going to do is row reduce this matrix to reduced form, not echelon form, or it's not reduced or echelon form, but it's echelon form. So I'll do row 2 minus row 1, then row 3 minus 2 row 1. So that's going to equal 1, 2, 0, 3, and still B. So minus row 1, 0, 0, 1, 1. And this is minus row 1, so it's B2 minus B1. And then we have minus 2 row 1, so that's 0, 0, 1, 1. And B3 minus 2 B1. And then we'll do row 3 minus row 2 is row 3. So that's going to give us 1, 2, 0, 3, B1, 0, 0, 1, 1, B2 minus B1, then 0, 0, 0, 0. So this is B3, then minus 2B1 plus B1. So minus B1, because we're subtracting the second row. So minus or minus B1 is plus B1. We have a negative 2B1, so that leaves a negative B1, and then minus B2. And just ask in the comments or in the live chat if you have any questions about that. So this becomes our constraint equation because that whole row is 0. So if this was we were looking for the equation of the plane, it'll be x3 minus x2 minus x1 equals 0. So we're looking for so these are the pivots. So I'm going to make sure I pick the right ones. So the column space is the columns of A matching pivots in the reduced form. So the pivots are in the first column. So that means it's 1, 1, 2. And there's a pivot in the third column. So that means 0, 1, 1. So that means the column space are these two vectors. So the column space, columns of A. The row space, rows of reduced form, except 0. So the rows of the reduced form, except the zeros is the row space. So row A equals 1, 2, 0, 3, and 0, 0, 1, 1. So this is the row space. The null space are the x that solves ax equals b. When I guess I should just say, instead of adding an extra step, ax equals 0. So we've already solved this here. All we have to do is make all the b's equal 0, and we solve that. So if we make all the b's equal 0, then this is still true. So we can say x1 plus x2 plus x4 equals 0, and x3 plus x4 equals 0. So x equals x1, x2, x3, x4, which equals negative x2 minus x4, x2, negative x4, x4. So all I did was just solve for x1 and x3. So that's going to be x2, negative 1, 1, 0, 0, plus x4, negative 1, 0, negative 1, 1. Let me see if I missed any numbers here. Yeah, I didn't write a 2 here. There's a 2 right there. So here is a 2. So here is a negative 2. And did I not write another number? I didn't write my 3. I was focused on the negative signs. I didn't write my coefficients. All right, so that seems to take care of everything. So that means that the null space of these columns that we end up with, so the null space equals -2, 1, 0, 0, and -3, 0, -1, 1. That's a null space. And the constraint equation is the left null space. So the constraint equation we got is this. So we can say n of A transpose equals constraint equations coefficient. So the left null space equals, and then 1, -1, -1. All right, let me check my answers and make sure I got everything correctly. Left null space. Oh, and I swapped my negative. The left null space, -1, -1, 1. Make sure you look out for the negatives. The null space is -2, 1, 0, 0, -3, 0, -1, 1. The row space is 1, 2, 0, 3, 0, 0, 1, 1. And the column space is 1, 1, 2, 0, 1, 1. So now we can do what I was talking about earlier, and we can check theorem 4.6. So theorem 4.6, to show that again, right, is this theorem here. So let's see if the dimensions of R, the dimension of the row space equals the dimensions of the column space, and it is the rank of the original matrix. So we have two pivots. So the rank of A equals 2, and 2 equals R. So does the row space have two vectors? Yep, the dimensions is 2 equals R. Does the column space have two? Dimensions equals 2 equal R. Does the dimensions of the null space equal n minus R? So in this matrix, m by n equals 3 by 4. 3 rows and 4 columns. So does 4 minus 2 equals the dimensions of the null space? So 4 minus 2 equals 2 equals n minus R, and that equals the dimensions of the null space. And m minus R equals the dimensions of the left null space. So m is 3 rows, minus 2 equals 1, equals m minus R equals dimensions of the left null space. So everything works. So the dimensions of the row space and column space is the rank. The dimensions of the null space and left null space are complements of each other. So when you add them up, they equal m. N minus R and m minus R. Oh, maybe they don't always equal and when you add them. But we know it's n minus r, n minus r. And then the null space will have more. So this seems to be true. So that was the four fundamental subspaces and confirming that theorem. So while we're here, let's see what else we can do. What's theorem 4.7? Nullity rank theorem. Let A be an n by n matrix, then null A plus rank A equals n. So let's check this. The rank of A is 2. The null spaces. So we have to see what they mean by null A. An immediate corollary of 4.6 is the following. The dimension of the null space of A is often called the nullity of A, which is denoted null A. The dimension of the null space of A. So we know the dimensions of the null space of A are 2. So I don't see how this one, okay, I forgot n is 4. So the dimensions of the null space of A, so corollary 4.7. Right? So the dimensions, null A equals dimension of the null space plus the rank of A equals n. So the dimensions of the null space in this case are 2. The rank is 2 equals 4, and it does equal n because this is an n by n matrix or 3 by 4 matrix. So n is 4, so that works. All right. So it goes to theorem 4.9 that V in Rn be a subspace. So V is a subspace of Rn. Then every vector in Rn can be written uniquely as the sum of a vector in V and the sum of a vector in V perpendicular. In particular, we have Rn equals V plus V perpendicular. So V is a subspace of Rn. Okay, that makes sense. So V doesn't necessarily span Rn, it's a subspace. It would have, I guess, normally less dimensions than Rn. So since V is a subspace, that subspace plus whatever is orthogonal to that subspace will span Rn. It makes sense. Let me write that. Theorem 4.9. V is in Rn. It's a subspace. All V that's in Rn Rn equals V, which is the subspace, plus perpendicular to V. That makes sense. Because the subspace is limited within that dimension. The perpendicular to that subspace, those two basically form a basis. And if you notice, the subspace goes in all directions. So this is a subspace. So this subspace has any vector in any direction. So I think my screen froze. One moment here. See if I can fix my. There we go. So notice that V, this is the subspace V, subspace of Rn. A vector can go in any direction here. So any vector added to the orthogonal vector. So now it could span anything in this entire space three-dimensionally. So we're taking R3, and V is a two-dimensional subspace. You take the orthogonal to that, and now you have a three-dimension. So it's simple enough. So Rn is spanned by the subspace plus the perpendicular to the subspace. Easy enough. So the last thing we'll do right now is example 5. We'll take a look at it. So example 5 says V is spanned by these two vectors, which are in R4. So you have the two vectors, each of them have 4 components. That's why the vectors are in R4. But the space is spanned by two vectors. So it's a two-dimensional space, two-dimensional subspace of R4. Still getting used to these dimensions that are made of multiple dimensions. Given an arbitrary vector B in R4, we wish to express B as the sum of a vector V and a vector perpendicular to V. Letting A equal 1, 0, 1, negative 1, 0, 1, 1, 1. So all they did was make a matrix out of those two vectors. We see that V, the subspace of V is the row space of A. Okay, because we have two pivots, we can't reduce it anymore. So now we know we're in echelon form. And the rows of echelon form, as we saw earlier, is the row space. Okay, so that makes sense. So since the row space is what we have, the null space is going to be orthogonal to that. And the row space spans V. Those vectors span V by definition. So the row space spans V. So the null space will be perpendicular to that. So this is what my professor was saying, what I was asking him about yesterday. The row space plus the null space spans the entire space. So now all we have to do is find vectors that give the zero vector. They gave negative 1, negative 1, 1, 0. So I multiply that in, dot product the left one in. I'll have negative 1, 0, 1, 0, that equals 0. And we have 0, negative 1, 1, 0, that's 0. Trying to right vector, that's 1, 0, 0, negative 1, so that is 0. We have 0, negative 1, 0, 1. So V3 and V4 are in the null space. To give the coordinates of B and R4 with respect to the bases, we can use a Gaussian elimination. Okay. So now it took vectors v1, v2, v3, v4. So now we have the row space and the null space all in one matrix. And use Gaussian elimination. And they're saying they can use a Fourier way to arrive at the answer because v1 through v4 are mutually orthogonal. If b is the C1 v1 through 4, we can dot this equation with vi to obtain ci equals b dot vi over the magnitude of vi squared. So I'm gonna have to look at that one more closely. So this is the row space, null space thing. So we know the row space is flat, the null space is orthogonal. The column space is flat, the left null space is orthogonal. Right, so this is all we need to do for this section. Even though I'm not familiar with the Gaussian elimination, so I'm going to have to make a note of that. I don't think we have to actually give the coordinates in terms of B. Let me search for Gaussian elimination. Spell it wrong. I don't know why I wouldn't me find the thing by searching for the whole thing. And it's way back in uh chapter 1, section 4. So apparently I need to review that because I don't remember Gaussian elimination. Seeing that. Trying to find this one spot, but apparently there's not just a quick. Okay, here we go. Our strategy now is to transform the augmented matrix of any system of linear equations into echelon form by performing a sequence of elementary row operations. The algorithm goes by the name Gaussian elimination. First column that does not consist of zeros. First column, but may not be. Pick a row whose entry in the column is non-zero. Use the uppermost row. And to change this row with the first row, not the first entry of the first non-zero column is non-zero. This will be our first pivot. Next, we add the appropriate multiple of the top row to all the remaining rows to make all the entries below equal to 0. Oh my gosh. I was not familiar with the term Gaussian elimination, but apparently he's just doing what we normally do. So why did that one look so different? The one that we were looking at looked extremely different. See if I can scroll back easily to that last example. Guess I would have never guessed that that would have ended up being. So let's take a look at this. You subtract the first row. First one is 0. Then you can do the second row. Let's see how that could equal 0. So apparently the third row, it doesn't look like it, but probably doesn't take that much. Probably because I'm not used to dividing by 3. It's like I have to give 1/3 up in there to make it work. All right. So row operations, they call it Gaussian elimination. Easy enough. All right. So we finished this section. I'll be back tomorrow to get the next section, and I'm working on getting through all the sections that deal with the homework that I have due next week. So look forward to me tomorrow. We'll keep this rocking, and hopefully your linear algebra is improving as well. Thank you for joining. Like, subscribe. Help me get to 1,000 subscribers by December. That's the goal. And see you next time.